here you may see a short outline of my presentation. So I will start with discussion of what are the gamma binary systems, and I will discuss two main scenarios for these sources. After that, I will discuss the non-thermal emission production in binary system from a phenomenological point of view, and at the end I will discuss something more grounded, like kind of modeling of two different aspects of this system. And the first will be quite general discussion of binary pulsar system, and another point will be discussion of the absorption in binary systems. And here I start. You may see sketches of two binary systems detected with CAS at very high energy regime. The binary pulsar PSR B1259 and binary system LS5039. As you can see, even from these sketches, these two systems are extremely different. And for example, look here, the orbit. Of course, they contain the basic elements like optical star. We have massive optical star in each of the system, and a compact object orbiting this star. But otherwise, these systems are quite different. So here we have almost a circular orbit, and here the orbit is extremely elliptical. And if you will look at this object which marks stellar disk, you will see that okay, in this system there is a star with a very dense equatorial outflow, and this stellar disk affect all the possible non-thermal processes in the system. So basically the only common point between these two systems that they emit gamma rays, and these gamma rays were detected. And actually there are not that many gamma ray binary systems. Here you may see the full list of these systems. And if you will look at the parameters, you will see that all of them, they indeed quite different. They have different scales, they have different geometries like shape of the orbit, and geometries in terms of orientation in respect to the observers, inclination angles. They have similar but still different luminosities of the stars. These stars of different types. You see two systems with O stars and two systems with B stars. This system even present very different TV signals. For example, in two of them we see a really periodic signal. In one, this PSR 1259, the signal is variable, but it seems not exactly periodic. And in the case of Cygnus X1, the TV signal was just a one flare, which was detected with magic telescope. Another important point that the nature of the compact object is quite different. So it might be either pulsar or black hole. And in these two systems, it's not clear what is the nature of the compact object. And so this suggests two different scenarios for gamma ray binary system. The first one is called binary pulsar system, and that's basically an idea is very simple: to have a scaled down version of pulsar nebula in binary system. And actually this scenario is very attractive because okay, first of all, there's this nice model by Khangulyan which explains the emission from the crab pulsar, and this model works in a way that pulsar itself ejects characteristic wind, which interacts with surrounding medium, form a termination shock, the particles are accelerated at this shock, and it forms some nebula, and basically the emission from this nebula is detected in crab. And actually, only recently the pulse itself was detected at very high energy regime. Previously, the very high energy emission from the pulse, crab pulse is coming from this nebula region. And in this way, it was very attractive to put this scaled down version of this thing to a binary system. We have a perfect target, the soft photons from the star, and we may detect much more gamma rays from this system. And basically, we just want to have something similar to Crab Nebula, but scaled down to a system. And here is a sketch of the object. So we have a star, it produces this stellar wind. Pulse itself produces the alternative pulsar wind. They collide, and in this collision, there will be some shocks, and these shocks may accelerate particles, and these particles should produce non-thermal, very high energy emission. And somehow to clarify possible confusion that this binary pulsar system, because there are many binary systems containing pulsars, and then I will speak about binary pulsar system. I will not speak about systems similar to PSR-B in 1913, where a pulsar and an optical star orbiting each other with a very small separation distance. It's not a binary system containing two pulsars like this one, and that's not a accreting binary pulsar system. The metaphor from the optical star penetrates very close to the pulsar, and even accretes onto the surface of the neutron star. So I will speak about this system, which are relatively big systems. So we may have there indeed like a pulse nebula. So with all its components, like pulse wind, termination shock, and this post-shock region. And another scenario is microquasar scenario. And here you may see a definition of the microquasar. Anyway, so microquasar is simply a radio-emitting X-ray binary displaying relativistic radio jet that can be imaged at a variety of angular scales using blah blah blah. And I think it needs some kind of explanation. So X-ray binary, it means that it's powered by accretion. And the radio emitting, it means that okay, there is a population of non-thermal particles which emit radio emission through synchrotron channel. And radio jets, that's okay. In this system we have jets. And actually this system is as well very attractive for production of non-thermal, very high energy emission. Because, okay, we have non-thermal particles. We have perfect target for inverse Compton scattering, the donor star floating field. And these particles may be accelerated at the jets. So that means there's a way to transport these particles relatively far from the system to avoid absorption, strong gamma-gamma absorption. So in this way, microquasars look as well quite attractive for production of non-thermal emission, very high energy non-thermal emission. And here you may see kind of artistic representation of microquasars. So the donor star, the matter from the donor star accretes to the compact object, which should be a black hole or neutron star. It forms a accreting disk, which emits this thermal X-ray emission, and it launches jets. And these jets look like a size of acceleration of particles. And if we look again on this plot, you may see that in these two systems, the nature of the compact source is not, let's say, finally established. Because actually, in some sense that's not that easy to establish this thing, because there could be some criteria like mass of the compact object, because pulse cannot be very heavy. Like if one detects pulse emission, it indicates that there is a pulse in the system. Or if one detects the thermal X-ray emission, it is a clear indication on accretion in the system. Or one can discuss the properties of the non-thermal radiation detected from the system. But strangely, all these arguments, they quite complicated in a way that to measure the mass of the compact object, we need to perform really very precise observation of lines. If one does not detect pulse emission, it does not mean anything again, because the pulse emission may be absorbed in the dense surrounding of the system, in the stellar wind or so. If one doesn't detect the thermal X-ray emission, the question is at which level should be this thermal emission, and it may be, again, it's quite a complicated issue, and the properties of the non-thermal radiation. Well, there are indeed many impacting factors, and as an example, I would like to show you these two light curves, and these light curves are obtained in two different scenarios, and you see that they in some way they're very similar. They have two bumps and like similar level of variability, but this variability is caused by very different physical mechanisms. And to distinguish between pulse and microquasars from non-thermal properties, one needs indeed very detailed observation. And at the moment, there are, and as well, very accurate modeling of the system. And at the moment, these things are not available.
Is this a model or?
Sorry?
Is it observations or model? Or?
No, that's model calculations.
Mm-hmm. So what is doing the absorption?
Huh?
What is doing the modulation? Is some
mechanism
of absorption?
Well, here the modulation is caused by the gamma-gamma absorption and angular dependence of the inverse quantum scattering. And here it caused by like hydrodynamical impact. I will discuss that later. So, but since we know that there is a very high energy emitter in this system, we may try to understand how this emitter can work in the framework of this system. And the most interesting part, that's TV emitter, because in a way that's kind of very ultimate thing, because it's the highest energy particles produce this emission, and it may be much more conclusive to discuss first the properties of the TV emitter in the system. And first of all, one needs to understand which mechanism may be responsible for this emission, and to evaluate different mechanisms, it's worth it to introduce radiation efficiency. Because if there are high energy particles in this system, to produce TV emission, first of all, we need to confine them, and second, to provide them some kind of target to produce TV emission. And we may introduce this radiation efficiency, which depends on the escape time, so how long one can confine particles in this system, over the cooling time, so interaction time. Depending on the target density, particle will cool with different time scales. And if we compare this escape time scale to the cooling time scale and multiply by the energy transfer, because at each interaction event only a fraction of the current particle energy is to be transferred to the gamma ray. And for different mechanisms, this fraction is different. But introduce multiplying by this energy transfer fraction, the ratio of the escape to the cooling time, we're getting some kind of general rotation efficiency coefficient. And we may check, for example, inverse Compton scattering. We have the cooling time. We have energy transfer, which is basically all the energy in the Klein-Shiner regime goes to the gamma ray. And for inverse Compton scattering, we're getting the rotation efficiency close to 1. In case of proton-proton interaction, the cooling time is relatively long because even for quite dense target, and the energy transfer is the gamma ray obtains only 10% of the proton energy, and in this way we may get this rotation efficiency for PP interaction. Checking in the same way P gamma interaction and photo disintegration, we're getting these coefficients, and if summarized, one may see that okay, in terms of gamma ray binaries, the best mechanism is inverse Compton scattering, and it's indeed quite easy to understand because we have very good target, which is the soft photons from the optical star, and we need a relatively small energy of the parent particle. So to produce TV gamma ray, we need only TV electron, and so it's easier to accelerate them and easier to confine them. So, and since we defined the TV emitter nature, we may discuss these emitter properties in terms of acceleration and losses. And in principle, there could be many acceleration mechanisms which can act in binary systems. But it's rather complicated to choose one of them. But we may try to make something very general to compare the acceleration with losses. And if we compare acceleration rate to loss rate, we may get some kind of limitation on the maximum energy of the particle, because indeed if particle loses more energy than it gains, like it cannot be accelerated above a certain limit. And if we'll combine all these conditions, which are here, we have acceleration time in quite general form, Hiller's criterion, which is basically the size of the accelerator must be bigger than the zero radius of the particle, and the losses in inverse Compton losses and synchronous losses, we may combine them in a plot, like in 2D plot, which here we have the strength of the magnetic field in the accelerator, and here we have distance to the optical star, because distance to the optical star defines the rate of inverse Compton losses. And basically, since has detected like 30 TV gamma rays from this system, we may limit the possible parameter space for this system LS5039 by this line. So it means that using only the TV observation with Hess, we may limit the possible magnetic field strength and location of the production area, distance of the production area to the star. And to go further, we need some information from multi-wavelength observation. And in case of LS5039, it was observed with Suzaku Space Telescope Observatory, and that was a dedicated observation, so the 1.5, 1.5 of the orbit was covered by So, and because of good sensitivity, one obtained like good light curves and the spectral index variation, the photon index variation over the orbit. And here you may see the results obtained with Suzaku Observatory. And interestingly, if you will see at this X-ray light curve, and if you compare it to the Hess light curve, they look very similar. Like both signals are periodic, and there are many like apparent similarities, like some kind of bumps near the pastron, and here's some kind of bump as well. So, and both, interestingly, both spectra are quite hard, and you would combine this TV observation and X-ray observation, we may see that okay, the properties of these in these energy bands, they're similar, but they are not exactly identical. And so here you may see this summary.
Do you see any variation in the calendars of the X-rays?
Sorry?
Do you see any variation in the absorption calendars?
Well, that's a complicated because the column density is more or less constant, and actually it's even like there are some variation, but like it's not consistent with like a simple expectation that the object is behind the system. We're getting significantly higher column density, but it's like more or less the same. But it may be caused by number of effects. For example, like the hydrodynamics of interaction. I can show some transparency which may explain this thing later.
What about X-ray and TV luminosity? Are you going to mention this somewhere?
Here and here.
These two observations both simultaneous?
No.
So different
No.
2 years or so?
There was like two years difference. Actually, it was planned to be simultaneous, but because of the bad weather condition in Namibia, Hess could not perform the planned observations. And it's interesting. So we have these 3 energy bands. So actually, this system was detected with Fermi, but they have not released yet the real energy fluxes. So, and we have these 3 different energy bands. We have like different mechanisms which may be responsible for the production of the emission. And it's interesting to change the view, to go from the photon energy to the parent particle energy, to the electron energy, and from the fluxes to the cooling times. And so one can combine the same thing in this plot. Here here is the energy of the electron, so of the current particle, energy of the current particle. So, and this region may be responsible for the Hess observation. This region should be responsible for Fermi detection. And in case of Suzaku, there are 2 possibilities, that either it's produced by inverse content in the Thomson regime, but most likely it's produced by synchrotron. And interestingly, this Suzaku energy band overlaps closely with Hess energy band. And actually, they're very different in terms of photon energy, but in terms of parent particle energy, electron energy, they are very close. And in this way, we may discuss what is possible to produce both Suzaku and Hess emission in framework of one zone model. And actually, it looked quite quite interesting because both spectra are non-thermal. Both of them are produced by very hard distribution of particles because the Suzaku spectra suggest quite hard electron distribution, and in principle this population of electron may produce very hard TV spectrum if one will account for anisotropic inverse Compton scattering. And all this puts some limitation to the location and properties of the emitting region. So using the fluxes in TV and X-ray energy bands, we may, again, these fluxes are linked to the cooling times, which are indicated by this red line for synchrotron and this blue line for inverse Compton. So from the spectral shape, we may define the location of the production region. We may define the strength of the magnetic field from the fluxes, and actually, okay, we may put this like input in a very simple one-zone model, accounting for adiabatic, synchrotron, and inverse Compton losses. So, and from the observation phenomenologically, we may define almost all the parameters we need to put. And if we'll compute all these things, we get like, that's indeed a very simple model. Like, we may get more or less X-ray fluxes at the required level, the TV fluxes, the more or less the shape of the TV spectrum, and we as well will provide some prediction for the Fermi. And in principle, so it looks like these multi-wavelength observations are consistent in framework of quite simple one-zone model. So, and it suggests to go for more detailed studies of the source. And
I mean, how do you know the size where you have the synchrotron emission?
sorry,
How do you know the size and the magnetic field? What do you put in?
the size, it's like the size is basically we have limited by the gyro radiuses. Like, because we know that TV emission is produced because of the spectral shape of the TV emission. We know the interaction angle with the soft photons. So, and in this way we may locate the production region in respect to the optical star, because we know the interaction angle of the photons and electrons which produce emission towards the observer. And in this
For that
way,
you need to know the inclinations, this kind of stuff.
well, we don't need inclination.
You don't.
Why? No. No, we don't need.
I mean, you have to know where is the star relative to you, right?
Well, because the
To
point
go.
that we have, like, we have the plane of the sky, we have orbit, we have the point if we say that okay, the emission is produced at the location of the compact object, then it's perfectly fine. We fix the inclination. But if we say that okay, we have some orbital plane, they possibly a jet, and this jet transport to some location, this thing. So, but we prefer to forget about all this freedom. We just fix the location of the production region in respect to the star. So just forgetting about the compact object inclination. So we just fix the location of the very high energy emitter here and optical star observers here. Like using the shape of the TV spectra.
The shape?
Like the spectral shape.
But you have not only know that this is Khangulyan spectrum.
What do you mean this is Khangulyan spectrum?
You said that's basically the spectrum. You said that Suzaku is gamma equal to 1.5. This is Khangulyan spectrum of electrons. So, what do you know else?
It seems I have forgotten to show the spectral measured with Hess.
Yeah, you did.
Well, I can show it later. And the point that this has measured. Okay, taken the like has like we have 100 GB has measured something like this for different phases.
So this is mu spectrum.
It's infinite. So, and it goes up to more or less 40 TeV. So, and this spectrum is like extremely hard. It's like,
So it's flat.
well, it's more or less -2.
And in Suzaku you have e to power you have e to power -1/2. 1.5.
Yes, exactly.
So it's harder.
Huh?
In Suzaku you have harder spectrum.
Well, the point is that here the inverse quantum scattering should be in the Klein machinery regime. So in principle the spectrum must be very steep. But the accounting for angular effects like inverse quantum, because we have a point, more or less point like source all the photons. So here electrons interact at certain angle. And effectively accounting for this angle, it may make the spectra harder, this TV spectra. But since we need small interaction angles for that, we fixed the location of the emitter. And the point that, like, accounting for this thing, we're getting something like pretty consistent in both energy bands. And that's not any kind of detailed modeling. It's like a very simple one-zone model. We just put an emitter in this system and like compare what one gets from there. So and it indeed suggests some kind of more detailed modeling.
Can I ask,
Yeah.
even if this is the case that you can constrain the geometry from the shape of the TV spectrum,
Yeah.
the TV spectrum is, so you measure something, you assume that this is a power law and you feed the model to the data, obtaining the index of the power law with some errors.
Yep.
So these errors, how they translate to the uncertainties regarding the geometry. Because, you know, let's say it has measured spectral index, photon index 1 plus minus something. Yes?
It has measurements of the photon index.
Yes.
Yeah.
So you say that knowing this gamma photon index, you
Yeah.
constrain the geometry.
Yeah, because we know that here in this inferior conjunction phase we need something very, very hard. And there is only one way to get this hard spectrum in the frame of this simple one-zone model is to make electron interact at very small interaction angles.
Yes, so I'm asking just about the number. So let's say for this error bar showing there, this angle is like, let's say 0 plus minus what? To give us some you know.
No, well, it's like you want to get the angle.
You
like-
said that you can constrain the angle.
well, we still have some freedom, but the point that Lucas, it's we cannot like we have a finite size of this star. We have this size, and of course in different regions we have different interaction angles. But roughly speaking, these angles should be small. And,
Yes, so my question is still, you know, how robust is this method? You said that from the spectral shape you can constrain severally. So how much freedom still you have, and how much is just like looking harder versus softer, and how much is really, you know,
well, I cannot somehow formalize your question in like common for me terms. Like, well, we still have some freedom. Like if I will say 10%, will we be happy? Not.
if this is what you get, that was my question.
Well, it's like more or less we can. The point is that like question of like quantitative modeling, but it's like a question of qualitative modeling. So whether we can get this qualitatively these things, but it's as far as I remember, there was like some kind of freedom, like maybe 10-15%. Like we can still move this thing, but it's like since we have nothing point-like, no, this angle, it's like if you locate the meter just here, it's like you're getting different interaction angles, but still, so if you move, it's not it does not change in average too much. So it's like 10-15%. I think you can easily move this stuff. And moreover, there's not there was no progress to like feed all the data. It was like qualitatively to understand whether it works or not. And in principle, like in this, somehow I will go to.
So what do you have here? The highest flux TVs, you have the hardest spectrum, right?
Yes.
You have photon index gamma 2, that's the highest flux.
Yeah.
And at the same time you have X-rays peak.
Yep. But
And this corresponds to what phase? What do you associate with this? What is the orbital phase of this?
this inferior conjunction.
Which means what?
Then the compact object is located between the optical star and the observer.
So this is the highest flux.
Yeah.
So basically, okay, so if you say that the one that's behind the optical star will absorb more
For
photons, and so
yeah.
the flux will drop. This is the interpretation.
Well, not exactly, but so as I said, all this recalls for a kind of more detailed modeling. And first I will discuss in this section the modeling of the binary pulsars. And okay, you saw this image, so we have crab. We want to have scaled down version of the crab, and here is the observation which has all the binary pulsar system B1269, and it was the observation discovered some kind of discrepancy between the earlier prediction. There was like 3 lines which are different theoretical prediction, and points has measurements. So, and basically none of these models is consistent with them. Has observation. So, and there was a like an attempt to explain the Hess light curve in framework of one zone model, accounting for different things like adiabatical losses, change of the shape of the accelerated spectra, and well, in principle, introducing some additional assumption, it's possible to pass through basically through all the points, but the point that like in any case, a one-zone modeling requires additional assumption, either adiabatical losses or acceleration efficiency. On the other hand, if one wants to introduce some kind of multi-zone model, so we need to understand how the pieces of this system connected to each other. And all these things recall for hydrodynamical modeling of this system. And in principle, it's rather complicated to predict the result of the collision of 2 winds, which one of ultra-relativistic, another one is non-relativistic, and there was a calculation, hydrodynamical calculation, and later there was a MHD calculation, so which were performed on this setup. We have pulsar which emits isotropic pulsar wind. This wind collides with the dense wind from the optical star. Somehow the pulsar wind is to be terminated, as well as the stellar wind, and we have like 2-dimensional setup for numerical calculation. The problem was assumed to be steady state, and actually the result was quite interesting because it looked like this binary pulse system works like a kind of muzzle. So it's like after the collision, the terminated pulsar, wind propagates in a very limited solid angle, and because of that, the pulsar wind may be accelerated up to very significant bulk Lorentz factor. So it's like here, formally one can get up to 100. And another result was that it's quite complicated to get the closed structure of the pulsar wind. Here, other parameter is the ratio of the ramp pressures of the stellar wind to the pulsar wind, and even if the stellar wind is 100 more powerful than the pulsar wind, the termination shock is still unclosed, and one gets still very significant acceleration. And even like we go even further, and if finally they assumes extremely powerful stellar wind and gets the termination shock located in the system, so that this wished compactified nebula, but still the acceleration or bulk acceleration of the flow is quite significant, up to bulk Lorentz factor 3, so which implies a very significant.
Can you explain the acceleration? Is it like
Muzzle.
hydrodynamical acceleration of the wind?
Hyperdynamical acceleration.
Because of the pressure of the nozzle, some nozzle?
Yeah, well, it's basically it works like you meet
Can you
particles.
explain this plot? Like, what is zero? Zero is a location of the pulsar,
Zero is location of the pulsar.
and the star is.
Star is located at 1, which is in this scale somewhere over there. There. And the stellar wind is very dense, so the ramp pressure is 10 to 4 times higher. And basically, all the terminated flow from the pulsar start to propagate in a very narrow line. And basically, because of that, it accelerates. It's like, indeed, I think it's a muscle or so. And if this thing recalls for accounting for Doppler boosting in the then one calculates the non-thermal output from this wind. And actually, the first step to see which kind of losses will be dominate, and using the hydrodynamical simulation, we can calculate the adiabatical losses in the flow, and it seems that the non-thermal particle population will be dominated by adiabatical losses, and we can calculate the synchrotron emission, like implying the MHD calculation. There was toroidal magnetic field was assumed in the pulsar region, and we assumed some accelerated spectra at the termination shock. These non-thermal particles start to propagate in this shocked region, and the magnetic field got enhanced, and the particles produce synchrotron emission, and basically the synchrotron emission will be produced from this region. And I would remind that actually this region propagates like this. So we're getting like a cone like this, with the most part of the synchrotron emission produced in this narrow region. And if we'll assume some inclination of the orbit, and we'll account for the observer which look at the system from the different directions. So we have this cone, which is here we have a pulse, and here a star, and this cone orbits. And sometimes the line of sight gets right here, and one gets enhanced emission because of the Doppler boosting. And this thing results in the light curve of this shape. Like these things, we have this emission, and it results in this kind of light curves, which so in this way, counting for hydrodynamical interaction in binary pulse, we nicely get a variable light curve. And actually interesting that in this case we'll naturally expect the correlation between all the energy bands, because the simply Doppler boosting of the emission, so the anisotropy of the particle population in a way. And
So what is the velocity behind the shock?
behind the shock velocity, so here, like, you may see that it's like velocity is c. Here is like bulk Lorentz factor.
Mm.
You have like a competition of, you have
That's about
c.
2 or something like that.
Huh?
So the Lorentz factor is about 2.
The Lorentz factor is, well, here is about 2 here.
Mm.
And like we may get a significant modulation because of Doppler boosting.
Mm.
Bulk Lorentz factor.
That's the same as in the crab.
Huh?
That's the same as in the torus of the crab.
Well, in terms of the crab,
It's about 0.5. The velocity about 0.5, but
well,
it's
velocity
a bit
is
faster than that in this case.
well, in case of crab,
Otherwise, it's very much the same.
we have this like shock wave, like shock wave like this, and one gets this pulse of wind which terminates like this, and here we're getting the enhancement of the magnetic field because of like magnetic field is frozen. We have like more or less constant density, and because of that you're getting enhanced magnetic field, and it produced this bright torus basically at 10 shock radii in case of crowd. Here is basically it's produced because of the enhanced magnetic field.
I thought the difference between the front and the back was also in that case because of what Doppler boosted.
Yeah, it's because yeah, in front and back again because of the Doppler boosting. But the speed of the flow is not that high.
No, it's the UC is about half or something.
So, and actually, it seems I'm running out of the time. So I have another section which, if you're interested, I may go on, or we can just skip it.
Depends what it is.
Huh?
It depends what it is.
Well, it's like discussion of the absorption in binary system and which kind of implication on the non-thermal emission it may have. Because in general, it's, to account for absorption in binary system, it's quite natural because we have a perfect source of target photons, and if one assumes that this compact object emits somewhere in the binary system, emits there is an emitter of very high energy gamma rays. These high energy gamma rays will interact with the stellar photon field, and basically it's very attractive because it gives natural variability, change of the spectral shape, but like skipping all these details, the point that that's not like simple absorption, simple attenuation, because all this energy is transferred to the secondary particles. And if there is an emitter in binary system, one has to account for another population of non-thermal particles, and unavoidably another emitting component. And actually this emitting component may get a very significant fraction of the total energy emitted at very high energy. And basically there are two ways of emitting of, like, either the secondary particles will interact with soft photon producing inverse component, basically a recombinant cascade will be developed, or if the magnetic field is enough strong, they emit in X-ray. And accounting for the conditions which one expects in binary systems, it's quite unlikely that they can be an effective cascade. So, and in this way, one may to think that, for example, this is a very famous radio observation of LSI plus 61 and 303, and which we discovered a quite interesting radio structure, which is not a jet, and it has a certain orbital phase dependence, and the shape of the images you may see here. But basically all of them are located around the system. So, and since this thing does not look like a jet, one believe that to be an evidence of binary pulsar nature. But actually, if since we know that LSI is a TV emitter, and that means that there will be a population of secondary electrons which will emit radio, and basically this strange structure and this secondary emission may be quite extended in terms of like a couple of astronomical units. So, and still maybe very significant, and maybe this structure means basically a very simple thing that LSI is just a TV emitter. So, and well, here there is like very general summary, which is like leptons are more attractive as a primary particles in binary systems. Image simulation are very important because they may have impact on the non-thermal production, and still there are many interesting questions, and there are like more detailed summary for modeling of 1259 and for this phenomenological study of X-ray and so on. Thank you very much.
More questions? One of you.
Okay, I have a question about time variability.
Time variability.
Considering if you compare these two different scenarios, the microquasar and the pulsar-driven scenario, would you expect any difference in variability properties? In particular, also considering that these three systems are quite different in size. The orbital size is very different.
Well, in principle, the real problem is the following: that there is no real model for microquasar scenario, because in case of binary pulses, it's quite easy because we have like pulsar which produces this wind, this wind interacts, and somehow at least we will know something. But the microquasars, we don't really know how things goes, and in terms of variability, like pulsar looks the only impacting factor should be the orbiting of the compact object. In terms of these classical microquasars, there are different states of the like this low hard state, high steep state, which are linked to the accretion regime. And in principle, in general, in microquasar scenario, one expects something like more stochastic variability, because it's linked to like accretion regime. And in principle, in case of microquasars, one may expect flares as detected from sigma 6.1. But the point that since we don't have real model for microquasars, I cannot answer
So
question.
rephrasing the question a little bit, for LSI plus 61, there is strong evidence for variability. If you look at one cycle to the other, there are variability.
Well, I would say it's even periodic.
What?
It's even periodic.
It is, I mean, yeah, it's periodic, the variations of the orbital period. But in addition to that, there are sort of flaring and variations from cycle to cycle, which is, that's what basis of my question. This variability, could one use that to say something about the pulsar-driven scenario, for example? I mean, there are inhomogeneities in these winds, so if there are inhomogeneities, I guess that can produce variability, but can one say something about?
Well, in principle, we believe that the pulses scenario should show like clearly periodic behavior of smooth patterns. But at the same time, the observation, for example, of this PSR 1259, they even cannot, they do not confirm the periodicity. like after another cycle, it seems that the flux at somewhat different level. So, and
But for 51 LSI, there are variations from cycle to cycle. I mean, you can see difference.
it's the same difference you can see in PSR
Mm.
59.
Yeah.
But they will.
But there will never be support.
Yeah, I don't know, but at the same time, one like expects something more smoother for pulses. And so the question is the point that the modeling is at the moment the modeling is at quite simple level, like counting for these like basic factors. One should get, like in case of pulses scenario, indeed periodic behavior. But even these observations with PSR, they show it's not the case, exactly the case. And it may be caused, for example, by thermodynamical instabilities. But it's impossible to count for at this stage.
Okay. Klaus had a question.
In this system, you have the E star, and they have very anisotropic winds due to the rotation. So it's, I mean, wouldn't you get the modulation just if the orbital plane is not exactly in the plane of the rotation of the star? Then you would automatically get the modulation of the emission, and might even get flaring in that case.
Point is, of course, it strongly depends on the properties of what is the ratio between the polar wind and the equatorial wind, like because in B star you have this like more diluted polar wind and extremely dense equatorial one, and if
You get focusing of the wind. You get focusing of the wind.
well, it's like depending on the scale where basically it's like decretion, like the point is you perform this aerodynamical simulation, you have like isotropic things, and you're getting this shape of the shocks, and if you implement here some outflow which is more dense, but not dramatically, just one gets an impact in this stellar wind termination shock, but it does not penetrate to impact this pulsar wind zone. So it's
well,
like
that's yes, but if the orbit is inclined to the
yes, I know, and
to
you
the
have
equator of the
this
star,
case,
then
and
you will get the
it
modulation.
penetrates.
The density will vary as a function of the phase.
Yeah.
You will automatically get the modulation of the light curve.
Well, but the point is not a problem to get. There are very many factors which even in this simplistic scenario, when you have isotropic winds, you're getting modulation of the light curve. For example, in case of, and actually the problem is that both winds are anisotropic, and in principle you have collision of two anisotropic winds, and the result is really hard to imagine. And
I agree with that, but at least you would expect to get the modulation
well, yes,
from that. Or, whether that explains all the observation, I'm not sure, but it's hard to avoid the modulation from.
No, in general, of course, you're right. That since you have anisotropic and inclined, and in case of PSR, we know that it's the orbit of the pulse is inclined in respect of the orbit of the disk. It's natural you're getting some additional modulation of this source. But somehow the purpose was to understand how this model works, like colliding, this purely colliding wind system, and which kind of, and actually, as you have seen, I was not comparing to any observation in case of colliding winds system, because there are many factors which potentially can have a very significant impact.
More questions? No? Okay, then we will thank our speaker again.